get locked in.
You're stuck there.
Alrighty. Welcome to, what month is it? August? August, gang?
September.
Oh, my bad. September, gang.
I know, it's August.
Still August.
It's more fun to
All right. Welcome to November, gang. Thanks for coming to the holiday party. We really appreciate it. Don't forget to be a sporting member, etc. In all seriousness, though, do actually become a sporting member if you're not, because the holiday party will be here before you know it. We'll also have slides at the end on like GameConf and .NET Conf and whatever else is going on around here. But for now, let's welcome Jason, who's going to talk about IoT. So, cool.
Thank you. All right, my name's Jason Follas. I'm an engineer at Quicken Loans, but nothing that I'm going to show you tonight takes place at Quicken Loans. It takes place a while back. And since this presentation has been running a little bit short, for some reason it gets shorter and shorter every time that I give it, so I padded it with a couple slides here to give some background into where this talk came from. So I'm actually going to open with a smaller talk, IoT with the ESP8266. So in my experience, the Internet of Things is kind of expensive. And I learned this when I was working for a startup. At the startup, we wanted to change the world, right? We wanted to have a device which can monitor the electricity that's flowing out of an outlet, so see how much electricity a lamp or any device that you plug into it was using, and then be able to report on that and give you some actionable items. And also be able to do things like if the kids left the fan on when they went to school, you could turn that off from work, you know, by seeing what was using electricity in your house. So this device that you see plugged into the wall there, that's nothing new. You can go to Amazon and buy any of 30 different types of these things. But we needed to build our own because we needed the data out of it. Those 30 that you can buy from Amazon, they're basically locked into their own ecosystem, their own app. There's nothing that's open about them. So that's why we were on the pursuit of building this device in order to capture that data to give you the information that you need. So the company's name was MeWatt. It's no longer a company because, as it turns out, it's really expensive to go through Underwriter Laboratory UL certification for a device that plugs into the wall. That's like the hardest certification to get. And every time that you try to get a device certified, you have to produce like 20 of them, send them in, pay $10,000, and then they'll go through a checklist. And when they come to one that fails, they don't run all the rest of the tests. They just tell you it failed at this point, and then you don't really get any guidance as to how to fix it. You just have to go back to the drawing board, fix that problem, repeat the cycle over and over again. Another $10,000, they might check that one off and then get to the next one on the list and say it failed. So we went through about 7 of those cycles. Wow. And this is producing 20 units at a time. So our offshore production line manufactured 20 units basically to be destroyed by UL. And then after that point, through a number of economic reasons, the company basically closed down. We gave up the pursuit of making this device. But there was a lot of lessons learned from making this device, and that's what I'm here to talk about. So our device had a really simple cycle. It had 5 second, every 5 seconds it would wake up, it would monitor or read the sensors that it was connected to, and it would send the data up to the cloud, and then it would sleep for another 5 seconds. So it just did that loop over and over again. So really simple. We needed a platform though. We needed something that could be the brains of this chip on the inside. So our first prototype was actually a Raspberry Pi. So we thought, well, maybe we can just take the important parts off of a Raspberry Pi and put those into our things. So a Raspberry Pi, with all these things, all the I/O that it has and the brains of it and the memory and all those types of things, runs about $40. And to strip the chip off of it and use the chip by itself, taking away all the I/O that we didn't need, it was still too expensive for our price point. We wanted this to be about $20 for the device, $20 or under, because it turns out that was a magic number for electrical providers. Like you have, who's up here? Do you have an Edison up here, or do you have, who's your power? Edison? Okay, so like Edison, but not in Detroit area. All around the country, there's all these electrical providers, and internationally also. And they all came back and said about $20 was their price point to be able to give these away as incentives to their customers. So that's why we were targeting that price point. So Raspberry Pi was too expensive. So we looked at Arduino. Arduino is really popular for IoT type of things. Arduinos are based around a microcontroller from Atmel. These are AVRs is what they're called, and they have like the processor and RAM and flash memory all in one chip, and that's this red big rectangle that you see down here. So we thought maybe we can build our system around the Atmel, but it was too underpowered for our needs, so we needed something a little bit more sophisticated than what this could provide. And that was $25, by the way, for this particular Arduino Uno R3 form factor. Maybe a little bit cheaper, you can go with the mini form factor of the Arduino. Again, it uses an AVR, which as you see in here, for $10. So this is getting closer to our price point, but at $10 for the brains of it, we still had little room for all the additional stuff that we had to put in, including the metering chips and all that kind of stuff. If we looked at Raspberry Pi again, they made a Pi Zero, and again, they stripped down all the I/O, all the unnecessary I/O, and just kind of have this base package. So again, we could have stolen just a center chip out of there and then reverse engineered all the connections that were needed. But $5 was still a little bit too expensive for something that we ultimately had to engineer. And all of those didn't have the I, right? Those were all devices, and you could build things with them, but they didn't have anything to do with the internet, no wireless connectivity. So what does it take to then pair one of those brains up with something wireless? Well, for the Arduino has a platform called the Yun or the Yun. It means cloud, I think, in Mandarin. This actually pairs an AVR up with another chip that runs Linux. So they're connected serially all underneath this hood here, this metal can. So you really have two processors. The Linux part runs all the Wi-Fi stuff, and then the Arduino part allows you to run your Arduino code, and they connect serially between them two. Obviously at $80 for this whole thing, it was too expensive to even entertain, but it was interesting to see the solution they took. There's a mini version of that, $65. As we get even lower in price, there's the particle photon, which has this one unit, this core unit that they can sell by themselves. That runs an STM32 Cortex M3. It has 128K RAM on board and a megabyte of flash, megabyte of flash RAM to store your code in it and stuff like that. Underneath this can, so you have that STM32 underneath there, paired with a Broadcom Wi-Fi chip. So again, you have two chips that are kind of working in conjunction with one another. One's the brains, one handles just Wi-Fi. We contacted Particle about getting just that core and see if they could get it down to our price range. The lowest that they could go, and they say that this is true for any consumer, regardless of volume, but the lowest they could go for just the brains part, just the brains module, was $11, which was still above our budget. Raspberry Pi had a wireless version for $10, so double the cost of the Pi Zero. You can get the Pi Zero W. And then this was interesting. So this little thing came out mainly through Chinese importers. So this is the ESP826601, and it was advertised as a serial to Wi-Fi interface. So you, from your brains, from your microcontroller, you would connect wireless or serially to this device and then send an AT command. So remember back in the modem days, if you typed ATDT and then all those things, it would have your modem dial into your internet provider or a bulletin board system. Same type of thing is used here. So you would issue an AT command to connect to an access point. an AT command to send information up to an HTTP web server, those types of things. And at $2, it was certainly attractive enough to pursue. So taking a closer look at what this little device had, it has 8 I/O pins, so you have like a transmit, a receive pin for the serial link, you have power and ground, you have a couple I/Os, and then you have like controls and reset. So pretty simple. And really when you look at what's on board here, you have this device, this microcontroller here, paired up with, this is just a SPI flash ROM down here. So this is the read-only memory for this thing. So certainly interesting, and at $2, that means that the components on this was probably cheap. So that was the 8266. And I think in the beginning, they really didn't know what they had. So they designed this chip, but they were using it for this serial interface, this clunky serial interface. And when people really dug down into what was on this chip, it was really interesting. So the 8266EX, all aboard this one chip here, you have a microcontroller, you have RAM, you have Wi-Fi, and you have GPIO, all on one chip. So we didn't have like the brains that had to be married up with a separate Wi-Fi. Everything was in one package, and when they're in one package, that means cheap. That means it's well within the constraints that we were working with. A company called AI then takes those chips and packages them into multiple form factors, into modules. So the 01 is the module that I showed you before, and then it goes on up numberings, and they all look like experiments. I don't know if they were hired to come up with these designs or if they had needs for them, but really, beside the 01, which was really popular, the 12 down here is the most popular one, and that's what we were looking at for our system. So it's really tiny. You know, there's a quarter, so you can see just how small it is, which was perfect because our device was really tiny. And for developers' purposes, they sell them in breadboard-friendly kits. So this is the module, and it's soldered onto this breadboard, and then these have standard 1/10 of an inch risers on them, or headers on them, that you can then plug into your normal breadboard and do things with them. So Adafruit sells the Huzzah, which is based on the 8266. They also have a form factor called the Feather. If you're familiar with the Feather, they have a Feather version of the 8266 for $16. A company called Wemos has the D2, which is $4. So for $4, you get this breadboard-friendly kit that you can just drop in and start playing with. And it's powered by, you can't see it here, but on the other side, there's a micro USB port, and that's how it gets its power and its I/O back to your computer. And then there's a form factor, an open source form factor, so you can go to GitHub and download schematics. And in fact, people have done that, and they've produced these things, and it's called the Node MCU, Node MCU Dev Kit. And it's just you can see how the same schematics leads to different variations. But this is what's the most popular. If you go out to banggood.com, a popular Chinese importer site for electronics and whatnot, you can buy these form factors for like $5 or so. So what's inside the 8266 that's so exciting? So there's a 32-bit RISC processor in there, and it's based on the Tensilica Extensa core. So Tensilica is like an American company, as far as I'm aware of their history. An American company in Silicon Valley, but their claim to fame is that they basically make Legos, like drag and drop and components that turn into silicon. That you can say, I want a microcontroller, and I want Wi-Fi, and I want RAM, and you just drag these onto like a design surface, and at the end it gives you it stitches all the connections together really easily and gives you something that you can go to manufacturing, and that makes the turnaround time for making something like the ESP with all this functionality built into it a lot lower, and that's why Espressive, who makes the ESP, was able to turn it around. So a 32-bit RISC processor. So 80 and 160. Out of the box, it's set to run at 80 megahertz. So anybody in here have a Commodore 64 back in the day? That ran at 1 megahertz. So this is 80 times faster than the Commodore 64. Or you can press the turbo button and take it up to 160. So, and it's software selectable. So if you need it to run at 160, and why wouldn't you not? Probably for power savings is why you would want to default to 80. But from a software switch, you can jump the clock cycles up twofold. Less than 1. That's the price of that small square chip itself. So when they're manufacturing it, it's less than $1 for that little chip that goes on. And then it gets more expensive as you start mounting that onto like the AI thinker board and mount that onto a dev kit. That's where the price goes up. But the chip itself is $1. 2, that's the price of the ESP12 by AI Thinker. 3.3, that's the volts that you need. So that might be a challenge if you're into IoT and whatnot. Most things are 5 volts. So it's important to know that while the I/O is 5 volt tolerant, the chip or the chip itself needs 3.3 volts. So on those dev kits, there's a voltage converter that will take your 5 volts from your USB and convert it to 3.3 for the chip's purpose. 80 and 35. So there's 80 kilobytes of data RAM and 35 kilobytes of instruction RAM running on the machine. So that's what you have available to you. 16 GPIO. There's 1 analog to digital converter on it, and it works in the 0 to 1 volt range. Again, only important if you need to know this stuff, or if you have the need for ADC. 802.11, it has BGN Wi-Fi built into the chip, but it's only 2.4, so it doesn't work in 5 gigahertz band range, which isn't a problem for most home electronics. And our system, our device, wasn't going to work with like a hub, like a smart home hub or anything like that. It was going to connect right to the person's Wi-Fi in their house. And then 30 million, a year or so ago when I made this slide deck, that's how many estimated parts were released. So the Wi-Fi, I said it was in the 2.4 band only. So that one chip can work as a station. That's where it connects to your access point. It can stand itself up as its own access point, which is useful if you need to configure it, because you just turn on its access point, start up a little web server, and then you can connect to it from your phone in order to set things like, tell it, here's my home Wi-Fi information, if you're configuring one of those devices. Or it can work as both. It can be an access point and a station at the same time. However, something to be aware of if you start working with the Wi-Fi and these things, there's only one radio in it. So if your home's Wi-Fi access point is on channel 11 and you try to stand up the access point on the little chip itself on channel 7, the station's always going to win. So the access point will actually pop up on channel 11 also. So you only have one radio channel to work with. And some interesting things. So given 2 Energizer AA batteries is about 30,000 milliamp hours. On standby, one of these ESP8266s can last 8.4 years, basically just sleeping or on standby. If you turn it on, and I'm not sure what load these things are under, so whoever did this study, his definition of always on, it ran for 44 hours. So I don't know if that's connected to Wi-Fi all the time or if it's mostly like idle or what the workload is, but 44 hours is what his test ran. And then if you put it to sleep and wake up every minute, then it can go for 18.6 days. And if you wake up every hour, it can go for 800, almost 3 years there, waking up just every hour. So imagine building a little device that you're putting out in the middle of the woods somewhere, just to do weather monitoring or something like that. If you wake up every hour, you don't have to change the batteries in that thing for almost 3 years. And then the firmware, and this is the last section before I get into the main presentation for tonight. So the firmware, there's a lot of grassroots efforts out there to write firmwares to run on the chip. So firmware is the software that runs the chip itself. So that serial, that 8266-01 module that I showed earlier with the serial link with the ATDT commands or the AT commands, that's the default one that comes on those chips out of the factory, on the AI Thinker modules out of the factory. So in order to connect to an access point, you would basically, from your microcontroller, send a serial command to the chip saying AT plus CWJAP, whatever that means, and then this string. And that would connect the device to the access point. So that's how you had to do it. Seems chunky, but if all you have to do is a serial port to work with, it does give you a way to do it. But Espressive released a couple SDKs so that you can write your own firmware. And this is where the grassroots community efforts have started. So there's two versions. There's one that they call the non-OS SDK, uses timers and callbacks, and this is very familiar, a very familiar paradigm, especially if you do like node programming, Node.js and stuff like that. And there's a real-time OS operating system. So on GitHub is where you find most of the firmwares out there, and they're basically based around languages. So there's a firmware which will allow you to run Python code to automate the I/O and stuff that's on those chips. There's a JavaScript one, there's a C++ one. There's even Arduino support. So there's a firmware which will turn this chip into an Arduino device. And in fact, they sell an Arduino Uno compatible form factor with that chip as the brains. So you don't need that funky thing where you have like a Linux processor talking to an AVR. You can do everything Arduino-wise with the 8266 directly for about $7. The one that we landed on though was, remember that Node MCU dev kit that I showed, that form factor I said you can buy for $5? Well, they made a firmware that goes along with it too. And this firmware exposes a Lua language service, so they use Lua, which is a language, to automate the IOs and stuff like that. And here's the stack. So at the very bottom, we have the device itself. We have the microcontroller plus the Wi-Fi. We have flash memory. And all of those are combined into the AI Thinker module. And then above that, we have the SDK, that callback non-OS SDK, or whatever they call that. And on top of that, there's libraries in this Node MCU firmware to automate things. Like if you want to talk to GPIO, then you have this GPIO module that they wrote. If you want to talk SPI, which is a serial peripheral interface, there's an SPI module. There's an MQTT module, which was attractive, especially as we go into the next section here. And then that's the firmware. The eLua is the language service that the Node MCU firmware exposes. And then our value add, so after we flashed that onto the chips, our value add then was we just had to write scripts in Lua to automate these things in order to do the information we want. So our scripts were basically wake up, connect to the person's Wi-Fi, read our sensor settings, broadcast it out to the internet, and then go to sleep. So that all happened in our scripts, and we were talking to these modules down here, these objects down here, which ultimately talk down to the chip level. So that's kind of how everything came together at the IoT level. All right, so that's the quick introduction. How many people did I lose so far? All right, so now that sets the stage for lightweight pub sub for web apps with MQTT. And you're like, that has nothing to do with web apps. We'll get there. And we're going to start back in 1998, or 1997 actually, with something that's called the petroleum pipeline problem. So this is what a petroleum pipeline is like, right? You have this big pipe, goes through the middle of nowhere. And when I say middle of nowhere, I mean nowhere. Like from Alaska, there's no cities hundreds of miles away. There's definitely no internet. There's no power to these things. But yet you have a pipeline running through it. There's pipelines all over the place, especially in our neck of the woods. You have upstream and downstream pipelines. You have upstream meaning from the well to the refinery, you know, how to get the raw petroleum there, or the crude petroleum. You have downstream, which is, okay, we just made gasoline. We have to get it out somewhere where the trucks can get it, or it's too expensive to truck it, so we're going to just pipe it from point A to point B, and then it can be trucked from there to the gas stations. All of those things are under our feet. And then we have to, you have to monitor it. So for a crude oil pipeline, every so often you have a station which looks like this. And this has a valve, so if they need to stop the flow of petroleum through there because there's a break, or maybe they for whatever reason they need to stop the flow of petroleum or slow it down or speed it up, there's a valve that they can command. There's also sensors in there for things like pressure and temperature. Sometimes there's pumps, especially if you have to go over a mountain, you have to pump the oil up high enough so that gravity can take over. All of those things happen at stations like this. There's a system called a SCADA system, and SCADA isn't just like it's not a product, it's kind of a generic industry term. So it's like saying a CRM system or something like that. So a SCADA system is what a petroleum company would use, and its purpose is to monitor all those sensors and also to issue commands like close the valve or turn on this pump, those types of things. And remember that all those systems are out in the middle of nowhere, so that comes into play here. Remember 1998?
Yeah.
Some people don't, but that was actually my cell phone. So it made phone calls at a time when I don't want to take a phone call anymore on my cell phone. The Apple just released this beautiful type of Mac. If you're lucky, you had a 56K modem. If you were unlucky, you probably had like a 24 or a 33.6 modem. And then Windows 98 just came out. The typical machine at the time was only a 300 megahertz Pentium 2. And remember that little chip I showed you could go up to 160 megahertz. So now you can kind of see why IoT is playing into this MQTT story. I had 120 megs RAM and 9 gigs of storage on the hard drive if you're lucky. So this slide comes from an IBM white paper about MQTT of all things, but this is setting up the stage for why MQTT came to be. So you have the SCADA system down there in the green and on the right side, and the SCADA system would connect to over satellite links to all these stations that are on the pipeline. So they had to use a slow satellite uplink from the field back to the SCADA system. And SCADA was using a polling paradigm. So they would actually go over the satellite and say, okay, temperature sensor 1, what's your reading? Wait for it to come back. And then it would go over the satellite and say, sensor 2, what's your reading? And go back. So it was really inefficient. And basically they filled up the satellite uplink. They had no bandwidth left to issue any more commands or to support any more stations along that pipeline. They filled it up, and it was really expensive back then. I mean, a cell phone plan was expensive, so imagine a satellite plan. And this is about the same time that Iridium was launching for satellite phones. They were launching that low orbit satellite constellation, but that wasn't really in place yet. So we're still talking like a HughesNet, which had a big 3-foot dish and bigger than a DirecTV dish, but a 3-foot and really low bandwidth also. So as you can imagine, it quickly filled it up. They also had this problem where other systems, like a billing system or a maintenance system, might be interested in that real-time data too, but they had to wait for SCADA to export it. So they called this the SCADA prison because they couldn't get to the data that they needed to from those other systems. So all of these things is what they were trying to solve. They needed an energy-friendly, low-bandwidth protocol that could feed information to the SCADA system over low-bandwidth satellites. They wanted it to be simple to implement. They wanted a quality of service. We'll talk about that. Because of the machines at the time, low processor and memory requirements. Data agnostic. They didn't want to define anything on the protocol. They wanted you to be able to send a picture just as easily as text. Session awareness is something interesting we'll talk about. If one of these stations goes offline, how do you know? I mean, without somebody going out there to the field and checking on it, they wanted to be able to detect when something went offline, which is interesting when we get into the web application side of it too, later on in the presentation. And also the very bottom one, they wanted multiple systems to be able to consume the data at the same time. They didn't want one system to receive all the data and then have to feed it out to the other systems. They wanted everything to hear all the information at the same time. So here's their solution. Ta-da, MQTT. Originally stood for MQ Telemetry Transport, and MQ came from IBM MQ series, which was their message queuing series. Invented in 1999, one of those engineers, Andy Stanford Clark, is still answering questions on the forums. So he's still out there in the IoT space today, even though this was 20 years ago. It was used almost exclusively internally with IBM until 2010 when they released it royalty free. So it was always a protocol used in conjunction with MQ series. But when they released it for free, they said, well, for legacy reasons, we'll call it MQTT, but it's no longer an acronym. The MQ doesn't stand for MQ series anymore. It's just a legacy part of the acronym. So here's the changes that they implemented as part of this re-engineering. So first of all, they fixed some of that polling problem by concentrating, using concentrators in the field. So those sensor stations would connect to nearby other sensor stations nearby, and a concentrator would do the polling that was necessary. And then the concentrator, instead of sending all that data up, it would just send exceptions up. So instead of something saying, always broadcasting that temperature sensor 1 is 100 degrees, over and over, it would only broadcast when temperature sensor 1 changed. So if it went from 100 to 101, that would be sent up. But as long as it stayed at 101 from that point forward, nothing else would be sent up. And that's how they were able to make the bandwidth more efficient. And then they used a message broker. This is the MQTT part. So a message broker then would allow systems to subscribe to those messages. So the concentrators in the field would publish, and then these systems, the billing system, the maintenance system, and the SCADA system, would subscribe to those messages. So they all three got the messages in real time as they came off of that broker. And that's basically the crux of the improvements that they did in order to be able to add more and more stations along the pipeline without introducing any more bandwidth up at the satellite part. So they use the same bandwidth, just more efficiently. So what is MQTT then? So in my definition, it's a binary-based protocol built on top of TCP/IP that enables publish, subscribe for machine-to-machine communication. So binary-based protocol makes it data agnostic, right? This is I can send a picture as a message just as easily as I can send XML or JSON or just a simple text. So being binary means that the protocol doesn't define what the message is. It's built on top of TCP/IP. That's important. We'll see that in a little bit here. Publish, subscribe, we'll talk about what that actually means. And machine-to-machine means that this isn't intended for humans. So when you're sending binary data, you can send whatever efficient data you need to, because a human's not going to read it. It's intended for another machine to read it. One important thing to point out is that even though MQ's in the acronym or the name MQTT, and it came from MQ series, it's not a message queue itself. So this is a wire protocol. This is like SMTP for email, right? This is how information is passed from clients to servers. It doesn't implement queues itself. So there still might be a need to pair this with a queue, just like they did with MQ series, but that's not out of the box with the protocol. It's now standard as of 2014. It's an OASIS standard. The current is MQTT 3.1.1, and version 5 is nearly ratified. So this year we should see version 5 be the latest standard for MQTT. Has some well-known ports. 1883 is unencrypted, and if you need SSL, 8883 is the SSL port, the encrypted version of it. So what is publish subscribe? So my IoT device, the thing that monitors electricity, that's what we're calling the IoT device, that's going to be the publisher. So that has the sensors on it. Every 5 seconds, it's going to read data from the sensors, and it's going to publish that up to the internet. So in this case, what it's talking to is a server called the broker. So it publishes how many volts and amps are the current reading off that sensor up to the broker. And then I have several systems that are interested in some of those messages. They're not always interested in every message, so they're going to subscribe to certain topics. And the topic is usually like this device's ID or the data that's coming out of this device. So I might have a web app, mobile device, and an application all interested in the real-time data that's coming out of my house. So I'm going to subscribe. I'm going to go through the broker for each of those and subscribe to the data so that when the data is published, then it's fanned out to all of the people that are interested in hearing about that data from that device. And that way my phone, which is monitoring my data, can get that real-time push just as easily as a web app can. But just because a device publishes doesn't mean that it can't subscribe also. A device can be both roles. So my IoT device down here, let's say that I want to send a command to it to turn off the switch, to flip the relay to turn off my kid's fan that's running in their bedroom. So my application then, from the application I say, turn off the fan on device 123. I publish that to the broker, and my device down here can subscribe to those messages because it's interested in hearing commands sent to itself. And that's how it gets back down. So the big point here is that publish and subscribe, or a publisher and a subscriber, is a role for a particular message, which direction it's flowing. But it's not a role for a device as a whole. So those brokers, that server part, originally there's only IBM, right? IBM's broker. But since that was released as an open standard, now you have a bunch of grassroots efforts out there to build brokers, or the server parts. And a lot of these are built along languages. Because when they build a broker, like let's say this Mosca, this node broker, which is what I'm most familiar with because that's what we were using for our system. So when they built Mosca, they built it in a way so that there was events that you could register. So when a new message was published, for instance, or if somebody logs in and connects to the system, you can do things like security checks. Security checks isn't formally part of the protocol specification, so you have to add that in yourself. And how are you going to do it? Well, if you're running a Node JavaScript version, you can just go in and set up your own event handlers to handle events as they come in. There's a Python, .NET, Erlang. The HiveMQ down there is advertised as a turnkey enterprise broker. So this is something that you can buy from them and turn on in your enterprise, whatever that means. I think that goes for SLAs is probably why they call themselves an enterprise broker. And then if you've ever heard of Azure IoT Hub or an AWS IoT Message Broker, those actually use MQTT as the protocol that sends data back and forth. And then they have their own value adds on top of that. So when we talk about the protocol itself, we only have to know 5 verbs. So part of the simplicity and part of the reason why this protocol can be implemented on something as small as that MQTT, or as small as that ESP chip, is because it's really simple in how it was implemented. So there's basically 5 verbs, and we'll talk about the parameters that goes along with each of those verbs. So when you connect, connections are always established from the device itself. So the client calls the broker can't call the client for obvious reasons. So when the client calls the broker, it has to pass a client ID, and that has to be unique for every device that's connecting. It passes a flag saying whether it's a clean session or not. You can pass a username and password. Again, MQTT defines that a username and password could be passed up, but it doesn't define how you handle receiving a username and password. So that's up to the broker implementation. Keep alive and last will and testament. So keep alive, this is how the broker knows if a device went offline. So when you connect, you define an integer, a 16-bit integer, of how many seconds the broker can expect you to be absent without sending a message. So if you say the keep alive is 10 seconds, that means every 10 seconds your device has to send a message to the broker, whether that's publishing something or saying I want to subscribe to a new topic, or if you don't send anything, then a special Keep Alive packet will be sent automatically by the client software. And the purpose is so that the broker knows that your device is still alive. If 10 seconds goes by and it hasn't received a message, then the broker is going to assume that your device went offline, and then it can do special things on your behalf. There's a concept called client takeover. So if the broker thinks that client 123 is connected already, and somebody else tries to connect as 123, then the broker is going to assume that the original 123 went offline. Maybe it was running on a cell phone and he went into a tunnel somewhere, or something like that. Some reason it thinks that the new client connecting is the same as the old one. So what it's going to do is it's going to shut down all the connections that were on the old one, and it's going to start a new connection with the new one. So that's called a client takeover. And that's why it's important to have unique IDs. Otherwise, if you have two devices with the same ID, they're just going to be taking each other offline as they're fighting to connect over and over again. And then there's something interesting called a last will and testament, and you provide this up front when you connect. Basically, what happens if you're running on a device and the battery dies, or you go into a tunnel, or something like that? The broker sees that your device went offline. Well, you can have a special message that is sent in that case automatically by the broker. So when it sees that your device is no longer connected, it's going to send out this one last message to whoever's listening for it. And that's the last will and testament. What we used this for was a online-offline status message. So when our device connected, the first message we sent was, a status for device 123 is online. And then our last will and testament sent the same message, but offline was the payload, so that anybody listening to that topic would know when we came online and when we went offline, because they would receive a message that said online or offline. All right, so that's connecting. So after you're connected, more than likely you have information that you want to publish up to the cloud or up to the broker. So when you publish, you have to provide a topic name, the quality of service, a retain flag, and then your payload. So the topics look like this. They're basically a path. They look like a directory path, except you don't need that slash out in the beginning. And then the slash delimiter then separates each part into something that can be parsed. So with this semantic, and the semantics are entirely up to you to define. So with this semantic, we say that this is pipeline number 3, pump number 1239, and this is the temperature sensor. Somebody receiving or somebody interested in this particular temperature sensor can subscribe to this topic, and every time that something is published to this topic, they'll receive that message out. The important note at the bottom is that this is case sensitive, so a capital P for pipeline is not the same as lowercase p for pipeline. My advice is just to use lowercase for everything. Then there's the concept of quality of service. So with a QoS, you have 3 of them. You have 0, 1, and 2. A 0 means at most it's going to be delivered one time, which also means that it's fire and forget, and if the message never gets through the broker, then nobody will ever know about it. QoS 1 means that it's going to get to the broker at least one time, and a 2 means it's going to get there exactly one time. So what does that actually mean then? So for QoS 0, I said it's fire and forget. So this relies on TCP/IP to handle the transmission. TCP/IP has some capabilities so that if a packet gets lost, then your machine will send it automatically, resend it automatically. So that's what QoS 0 is trying to do here, is just rely on the underlying network to guarantee that the message is getting from point A to point B. But there's no guarantee that it's actually going to make it there, because nothing is checking to see if it made it there. So this is good for debug, informational, things that are quickly replaced, those type of information, so that if one doesn't get there, it's not a big deal. For QoS 1, your client's going to keep broadcasting the same payload over and over again to the broker until it receives an acknowledgement back from the broker. So maybe if it's sending it over and over and it's not receiving an acknowledgement, the communication problem could be here, that the payload's not actually getting to the broker in the first place, or it could be on the second part. Maybe the broker traffic is getting lost trying to come back to the MQTT client. And if you think about going over like a satellite or some unreliable network like that, it's possible that either one of these is the culprit, and that's why QoS 1 was invented. So it's waiting for this acknowledgement to come back. Now every time with QoS 1, every time that the message gets published, the broker is going to send it out to all the subscribers. So your subscribers have to be tolerant of receiving the same payload over and over again, because the client's going to keep broadcasting it until it hears that acknowledgement back from the broker. And with QoS 2, this one is exactly one-time delivery is what it's aiming for. So it does the top loop, so it publishes until it gets a received record back from the broker. It's going to keep doing that over and over again. So the top part is kind of like QoS 1, but the broker is not going to release that message yet to the clients, to the subscribers. It's going to wait until the client sends another message, which is publish release. And then the client's going to keep sending publish release over and over again until it receives a publish complete back from the broker. So you have these two loops that happen, and you need two confirmations back from the broker in order to stop the client from broadcasting. Even if the client sends a publish release 100 times, the broker knows with QoS 2 to only release that message one time to the subscribers. But this is the mechanism that's built on top of TCP/IP to handle things that TCP/IP can't handle directly. So retain flag. When I publish a message, I can say retain this. So only one message can be retained per topic, and it's basically used for a last known good type of data. When a new client comes online and they subscribe to that topic, they're going to immediately get any message that is retained first. That way they don't have to wait for a new message to be broadcast up, because maybe in that 5-second broadcast loop that my device was doing, maybe a client came up right after it published. So instead of that client having to wait 5 whole seconds for that loop to come around again, they can get that message right away as soon as they connect. So that's the usefulness of the retain flag. All right, so that's publishing. Now the next verb is subscribe. When you subscribe, you give a QoS and you give a list of topics that you're interested in. Fortunately, for something like a pipeline where you might have hundreds of sensors and hundreds of topics, there's wildcards so that you can subscribe to multiple topics all at one time. There's a plus wildcard, which substitutes any one part of the path. And there's also a #sign wildcard, which substitutes from that point to the end of the path. So it matches anything for pipeline 3 down here. Just a more efficient way of subscribing instead of having to pass in a list of hundreds of different topics that you might not even be aware of what the topic names are. Back in the beginning, when the device connected, there's a flag that we could pass called a clean session flag. So when clean session is true, that blows away any subscriptions that might have been set up, and that and it starts the session from scratch, from fresh. But if you're just if you're running a client on your cell phone, for instance, and you go into that tunnel so that you lose internet connectivity, when you come back online, you don't have to set up everything all over again, and you don't want to blow away any messages that might be waiting for you to receive because you subscribe to them. You just want to resume where you were before you went into that tunnel. So on that reconnect, if you say clean session is false, then what's going to happen is that all of your subscriptions are already there. You don't have to set them up again when you reconnect. and any QoS 1 and 2 messages that were sent offline will be sent down to your client again, so that you can get all those messages. They were just queued up while you're offline. QoS 0, because it's fire and forget, those aren't going to come to you. You know, they're forgotten at this point. So why do we need a different QoS when we subscribe than what was originally published? The QoS is a relationship between one client and the broker itself. So in the case of publishing, if I publish QoS 1, that's just guaranteeing the communication between my device and the broker. The broker is almost acting as a subscriber to what I'm publishing in this case. Over on this side, maybe each application has a different need. My application up there doesn't care if it misses messages. It's just kind of listening to the fire hose. So it might subscribe to a topic with QoS 0. My web app down there, I might only want to receive each message exactly one time. So I'll subscribe to a topic with QoS 2. And then in this case, the relationship is that the broker is almost like a publisher, and each subscriber then is subscribing to the messages. So QoS is a relationship just between a client and the broker itself. And it can be different from what was originally published. All right, we're getting closer to the web story. But first, Facebook. Facebook users, a couple. You know that chat, how you can chat with people? That's Facebook Messenger, right? So you have this chat window that's in the website. If you're running on a phone, you probably have a separate Messenger app. And you can chat from the website to somebody's phone using their Messenger. So the first Facebook Messenger was written basically with calls into their API. But they were running into problems that they would send a message on a phone, and it would be like 5 or 10 seconds later that the message would show up on somebody else's phone because they had to route through that whole messaging back end. So they did something daring. With only weeks left, weeks meaning, I don't know, 2, 3, 4 weeks, they refactored it. They got rid of the old API calls that they were doing, and they went and used MQTT instead. And they decided on that because they were working on people's phones, so they needed something that was energy efficient, and they needed something that could be tolerant of going into a tunnel. All those same constraints that we had in the IoT world, which ultimately led back to the oil pipeline problem, suddenly became relevant in the mobile app world too. So great quote from Lucy Zhang from Facebook. By maintaining an MQTT connection and routing messages through our chat pipeline, we're able to often achieve phone-to-phone delivery in the hundreds of milliseconds rather than multiple seconds, just by switching their protocol to MQTT. So now, how about web apps? So MQTT was built on top of TCP/IP, but there's an interesting correlation with web app world with something called WebSockets. WebSockets has a browser that communicates with the web. Okay, so the normal way that a web browser works, just to level set here, is that the web browser sends a request to the server, who sends the response back to the browser, and effectively the connection is closed. Now I know there's some optimizations in there to keep the connection open, but think about that cycle over and over again. So the browser initiates it, and then the connection closes. So the server doesn't really have an opportunity to send something down to the client until the client calls back to the server again. So that's the traditional sense. So there's been a bunch of technologies invented to kind of solve that problem so that servers can communicate to the client whenever they want to. And WebSockets is one of those. So the way WebSockets works is that the client calls to the server, but instead of the response closing the connection, they kind of open up this pipeline that the server can send information to the client, and the client can send information to the server, and they can pass each other on the way so that there's this pipe that's established. And that pipe looks a lot like TCP/IP, or the purpose of using TCP/IP in sockets. So since it looks and behaves like TCP sockets, they, meaning whoever's maintaining a lot of these MQTT brokers out there, implemented MQTT over WebSockets in addition to TCP. so that if you have a browser, you can connect to an MQTT broker right from the browser, right from JavaScript. It's not supported by all brokers, but that Node broker in particular supported that, and that's why this was attracted to us. Because we wanted to have a dashboard which could get that real-time data back from as soon as my device sent the electrical data up to the broker, I wanted that to not only be saved to a database, but also to hit me in real time. So I'm subscribing to that same data feed that my back-end worker was, and I could get real-time data sent to my web browser. There might be more, but there's two popular JavaScript libraries that allows you to implement this. One is from the Eclipse project, and it's called Paho. That's the one that I'm going to show you tonight. And there's another one from the maker of that Node broker called MQTT.js. So it's basically the same type of backend that the Node broker is using. It's just intended for clients and running in browsers and whatnot. So here's the demo that I'm trying to drive down to. So I have up here a device running one of those ESP8266s, but instead of monitoring electrical, because I can't plug into like the wall and stuff like that, I have a little weather sensor here. So on this little SparkFun board, we have this sensor, this really tiny sensor, and it's the BME280, and it monitors humidity, temperature, and air pressure, all in that one chip. And it has different I/O. It has like a I2C and a SPI, different ways to connect back to my ESP. I'm using I2C to connect back, so I'm just using 2 wires is all that. A send and receive wire basically is all that I need back. So similar to my electrical story, my ESP is up here. It has a unique ID, so I'm going to use that as my client ID when I'm connected to the broker. And it's in a read cycle. So it sleeps for 5 seconds, wakes up, reads the sensor, publishes up, and then goes back to sleep. So what I'm publishing then is I'm publishing a lot of different things. I'm publishing humidity, temperature, and pressure individually as their own messages. I'm also publishing one message that has a JSON payload that has all 3 values at the same time. Just because sometimes it's, depending on what the subscribers want, maybe they're only interested in humidity, so they can subscribe just to humidity if they want. Or if they want all 3 for the web page that they're working on, they can subscribe to just one topic that gives them all 3 at the same time. So the web page then is a subscriber for that topic, and it's going to get the data as soon as it comes through. And this is where we get into demos. There we go. All right, so what's happening here in this demo? Well, you have this neat graph in the bottom, and you see that's this toast that's popping up every 5 seconds. That toast is showing you the messages. So my client subscribed to a message topic, and every time a message was broadcast or published from my device to that broker topic, it's coming down to the web browser here, and you're seeing it. So if I do something like put my finger over this chip to kind of heat it up, we should see that red line start to go up as it's reading. I know, real exciting. But thank you for that.
Yeah. Let me blow on it. Get the pressure going.
The other thing we can do here is
Man, forget it.
even though I'm a subscriber here, like I said, I can still be a publisher too. So from here, when I click say hello, you're going to see 2 things. You're going to see an orange box, which is the message going out. So that shows that I published a message to the broker. And right away, you're going to see the same message come in a blue box because I'm also subscribing to the same topic that I'm publishing to. So I'm going to click. And you see the message was sent out, say hello, and then message received, hello. So right from here, and running on this thing is Node MCU, the firmware, and it has a Lua script that's actually running this. This is on GitHub, by the way. There's a link at the end if you want to pull down source code for all this stuff. But the MQTT module is running on this too. So from Lua script, I'm able to tell the MQTT module, connect to my broker, and then every time I'm publishing, I'm telling the module, publish this data. So it's a really tiny client that's running on there. The other thing, notice that this is online. So I'm also subscribing to a topic, which is like a status, and then my device number is the topic name. So it's like status/device number. When the device connected, it sent the word online to that topic. And it sent it as the last, with a retain flag, so that if I close my browser and come back in fact, let me just do that. Let me reset. See how it got online right away? And right here, this message arrived, status online. So because it was retained, I didn't have to wait for this device to announce that it was online. I'm retaining it, so as soon as I connected, I got my status right away. But what if I pull the cord? Well, my device also sent a last will and testament to set this message to be offline. And the keep alive is set for 10 seconds. So here in like another second or so, the broker detected that it was offline. It sent this topic up here, which is my last will and testament, saying, hey, this device is now offline. And that's the mechanism to detect if one of your people went offline, which I think is really cool for a web app to be able to do that. And if I plug this back in, and I come back to here, there you see it went back online. But the cool thing, no, I don't know why I can't type in my terminal window. I was going to show you all the stuff that happens on boot up, but basically, as soon as power was restored, there was a 5-second wait on there, and that's a good practice with these chips, is to insert a wait when it boots up, because if something crashes when code starts running, you want to be able to recover it or go in there to a terminal and break in order to inspect different things. Otherwise, if it crashes on startup, it's a hard loop and you can't get out of it without reflashing the firmware again. So when I apply power, there's 5 seconds for waiting, and then it connected to the internet or my Wi-Fi, which is running on my phone's hotspot. And then after it was connected to that hotspot, then it started doing the read loop to broadcast things up. And that's the whole cycle. The last thing to show in this demo is what it takes to do the JavaScript part. And I have to find the right file. All right. So working with the PAHO library, the PAHO MQTT client, is that big enough for people back there? I changed the resolution on my screen, so now my fonts are a little bit smaller. So the first thing you're going to do is new up a client, and you have to pass the broker's, the broker URL, basically the server name, and then the port number, and then this is unique ID for your device or whatnot. Just newing it up doesn't connect yet, so we get the opportunity to change our client here. So we create a client instance, and the next thing we do is set up some callback handlers. So like when a message arrives, this function gets called. We're setting this up before we connect. Now we define a last will and testament. When you publish a message or when you're setting up a message in here, you create a new MQTT message. Here's the payload. The payload is just a word offline. I could have put the bytes of an image on here if I wanted to or anything like that. You also set the destination name. So this is the topic that's going to be broadcast to. Now we're finally getting to the point where we connect. So we're going to connect, and we're also going to provide some callbacks here. So when we successfully connect, the onConnect function is going to execute. If anything fails, we have an error handler. Our clean session is false. So any subscriptions that might have been established are still going to be there, and any messages that were waiting for me when I was offline are still going to be there. And then this is where you pass in the last will and testament. The reason, notice that we're not subscribing to anything yet, we're connecting. We do all the work in the onConnect method because we have to connect to the server before we can start like subscribing to topics and whatnot. So once we connected, this function gets called. And this is where we do things like subscribe to general, subscribe to status for all devices, subscribe to the readings for all devices. If I wanted to subscribe to a particular temperature sensor, I can just say client subscribe with the wildcard, or I can put in the actual device ID in there. What else to show? And then when a message arrives. So even though I'm subscribing to 100 different topics, potentially, only one function handles all the messages that are coming from my subscriptions. And I get this message object. So I have to do something. I have to inspect the destination name, the topic name that's coming in order to know how to handle this particular message. And then I can get the payload from the payload string. And then the rest of the stuff you can look at GitHub if you want to see how I implemented the charting and whatnot. But all of that happens. So when those messages come in, when the message comes in and you see the toast pop up here, this is basically what's doing it. So that's what's popping up this toast, is that functions executing, that callback's executing, and I'm just showing toast with the destination name and the payload string. And that's basically it for the demo. The GitHub URL's down there at the bottom. And really, that's it. My name's Jason Follas. So thanks. All right, now what? I can take questions.
Here you go, take questions.
Two questions. You got that? Questions? Questions are good.
I'm waiting. Yes?
So I didn't see any slides on security. How would you handle security for somebody who's trying to make an IoT device for the first time? And if the intention is to take it, seriously and go into production later on.
Yeah. So security is not something that is in the spec. So the spec leaves security up to the implementation. So what we did was basically when our device connected, so our device connects and it passes up a username and password because we required that. So the password part is arbitrary length. So what we actually did was each device had a JOT or a JWT that had like claims and it was signed. So that like had within that JWT we had a claim to say, and this is the device number. This is all the information that we needed to identify the device and the user and whatnot was in that JWT. So that then when that device was publishing messages up, or if that device tried to subscribe to a topic that we knew it shouldn't subscribe to, up in the JavaScript broker code, that's where we intercepted that subscription event or that publish event or something like that, and we checked the security at that point. So we said we pulled the claims out of the JWT. And we said, oh, this person is allowed to subscribe to this topic. So we let that go through. Or if a client tried to subscribe to a topic that they weren't permitted to, because maybe it was like an administrative topic or something like that, we could deny at that point so that they wouldn't get the subscriptions. So I don't know if that answers your question, but basically implementing security meant extending the broker ourselves. Yes.
The NIWAD example they were talking about, which is really cool at the time, I'm assuming Wi-Fi is the most readily available and everyone knows how it works and what have you, but did the guys or you yourself consider other options like LP1 and all that other stuff?
Yeah, so this was our minimum viable products, our MVP. So Wi-Fi was the lowest common denominator. That would be in what we were seeing as our customers' homes. Everybody probably had Wi-Fi.
Yeah.
If they didn't, or if they wanted to buy a router dedicated to just these devices, they could do it for $20 or something like that. Because Wi-Fi routers can be cheap. So for our MVP, we went with Wi-Fi. There's always a vision for different form factors, like instead of a single outlet, we were going to have a double outlet version, which would monitor both at the same time. We were going to have a power strip version, which would monitor every outlet individually. And not only the form factors there, but also our vision went out to Zigbee or Z-Wave or all those other types of things that you ultimately needed a hub, a smart home hub to work with. So those were always on the roadmap. We just never got past phase 1.
So what actually killed it was the UL spending?
In our case, it was because we were a startup. Our VC basically ran out.
Okay.
Without going into much more details, but yeah, UL killed us because UL is just a pain. And this was seriously, anything you plug into the wall, into your home outlet, has the most stringent ULs for good reasons, right? You don't want a device to burn down your home. And UL is the underwriter laboratory, so these are the people that certify for insurance companies, as kind of like a stamp of approval that, hey, this device won't burn down your home. So really weird requirements too. Our device worked, right? Obviously, because we felt confident to go to testing. So the device technically worked, but the things that we failed on were when you plug a plug into an outlet, there has to be so much resistance to be able to pull it out, because basically if your outlet's upside down and you plug something in, you don't want that plug to fall out. So to test that, they put prongs into the outlets, and then they hang weights on them, and they hang weights for 15 minutes, and they rotate 90 degrees, let it wait 15 more minutes, and they keep going over and over to kind of stretch out, see if it will stretch out, the plastic or deform. And then they plug the thing in, and it has to be able to hold with a certain amount of weight. And basically, one of our first failures was they plugged in their test fixture, turned it upside down, and it fell out because our plug deformed under that weight test. These are things that aren't necessarily electrical in nature, it's more physical, but still it affects the whole certification process. So those types of things, that was a $10,000 mistake. Well, plus, $10,000 was just to have one of their what do you call them, their testers actually play with our devices.
Did you know how to test before submitting?
They're published, but it's kind of hard without your own $1 million lab to replicate them. And there were services, and there are services out there which kind of helps you get ready for the test. So if you want to pay a service $10,000 to pre-test it before paying the $10,000 to actually test it, that's an option. And we worked with some of those, and the whole saga gets really painful as we were let down by our vendor, and we just, yeah. Yes?
I had a question about 5 years ago, I think Edison came through our whole neighborhood and put in smart meters.
Mm-hmm.
And for the life of me, I don't know exactly what they do, but I'm told that you can monitor the energy consumption in your home, and they can monitor how much power you're using every minute of the day, and that sort of thing. How were they doing that? I mean,
in very much the same way we were. In fact, the monitoring chip that we were using is the same chip that's in a lot of those sensors or a lot of those meters that are on the homes. They just, because they're monitoring your whole home at one time, their interface, the things that monitor current and voltage is scaled up in their case from what we're using, because we were only going 15 amps max, and they're probably monitoring up to 500 amps max for a typical home. So they had a little bit different wiring, but ultimately whatever that interface is to the electrical system boils down to coming into a little chip, and that little chip is what we're using as our monitoring chip.
but can't they shut down your air conditioner and things like that?
I don't think they have that type of functionality. I don't know what's in those meters. As far as even if they are able to transmit. I saw when we were researching all this, I saw where there was plans to be able to transmit over the electrical lines back to their house, kind of like how you can get these internet extenders for your house, where you plug it in one room with your router, and you can go plug this device in another room, and it basically gives you Ethernet out of that remote room, and it's going over your home wiring. So that technology exists to send data over power lines, and maybe they're doing that, but I don't know. Yeah.
I know one time they were sending out these boxes and they gave you the option to be able to download a mobile app and you could see your house, all the utilization. So I'm wondering if, and I got one, but I sent it back because you basically plug it into your network. I just felt uncomfortable plugging it into the box.
So is that whole house?
So what I could be happening is maybe that talks to your power meter, which feeds back to them, and then your mobile app connects to them. The data is basically a conduit through the
Yeah.
box that you're plugging into your Ethernet.
It could, and there's, I mean, monitoring your whole house is one thing, but we wanted like point of use for our situation. So instead of seeing how much of your 200 amp service you're using, we wanted to know how much this one plug was using and be able to control that one plug too. So our vision was you would have like 20 of our devices in your house instead of one device for the whole house.
I'm saying that box might have been there.
Oh, sure,
To get their data back to their company.
Yeah, sure. I was just expanding on my story because I thought I left that point out.
Typically, these are smart, they call it smart utility networks, SUN, and they don't run on the Wi-Fi in your house unless you put something there. It runs on 900 megahertz, it's separate, and most of the time what they use it is so that the person doesn't have to, the person from the utility company doesn't have to go to each house like you've seen them walk. No, they electronically, they just can't wirelessly, but it's just, and I don't quote him, usually it's just reading the actual meter read. Now, if you allow them to say, hey, you want to conserve energy, we have this amazing Wi-Fi solution, well, that's up to them if you want to do that.
I think they might even be cellular too.
It's too expensive to do on cellular, so what they do is ISM band, it's free, 900.
Well, I think like the DTU ones are cellular.
Because you would have to pay for a SIM card inside the smart meter, no. So there's a 900 good at ISM. It's a Wi-Fi on a different band so that you don't interfere with the Wi-Fi. The same thing. And or SUN. I know the e-tron one that we have in Troy, it's using SUN, but I don't know.
Yeah.
So just Google e-tron,
Well,
SUN. Yeah.
There's all kinds of stuff on the internet about it.
Yep.
Any other questions? Yes.
I still missed this. How do you subscribe from the web app?
I'm sorry.
How do you subscribe to this device from the web app?
From the web app, how do I subscribe to the broker?
Yeah.
That looked like. So after we connected,
Okay.
so on a successful connection, this callback gets called, the on connect. And that was set up when we connected up here. So we said connect, on success, call this function. So in there then, we just say client, subscribe, and then we give it the topic that we're subscribing to. So subscribe to the general topic. So any message that's published to general, this is going to make sure that it comes down to the web here.
So the MQTT is actually inside that chip, right?
MQTT, so MQTT is the protocol. So this is the data that's going over the wires.
Right.
There's a client running, so there's the server, that's the broker, and everything that connects to the broker is a client. So there's a client running on that there's a client running on here, and also this JavaScript library is a client that's running in my browser. So both of those are clients, they're doing the same thing. They can publish and subscribe, but they need that server, that broker, in order to do it. Yes, one of you, fight.
Real quick, is there any limits to how many subscribers you can have?
It's probably an implementation detail of the broker. So
But as many as you can.
I'm not aware of that being defined in the spec, so however much you can load up. And then brokers are also meant to be scaled out. So like you can have like a whole farm of brokers that all have some kind of backplane, maybe like a Redis server that they use to communicate internally back and forth to each other. That way your connection over TCP/IP might be to broker number 1, my connection might be broker number 2. If I publish here, it goes down to the Redis that all the other brokers can see it, and then they can get their messages and fan it out to their clients. So it's meant to be scalable in that way, but I don't think the spec defines that. That's all up to the implementation. So all those brokers that I listed early on, each one probably has their own way of doing it. Yes? I'm sorry?
Is there a limit to the payload?
Is there a limit to, I didn't hear him.
The
Size.
The
Size
payload.
of the payload?
Oh, again, I don't know that the specification defines that. I think that's up to the implementation of the client, because like my little chip here can't send megabytes worth of data. It has to use small packages. So so that has a limitation. And then the broker might not be able to accept a big, large, it might not be able to set gigabytes worth of data. So there's probably a practical limitation, but I don't know that it's necessarily defined by the spec. Yes?
What were you using for a broker?
On where? Oh, Mosca is what I was using. And it's just a Node app, and it's actually running here. So down here, I just have like console logs every time a message comes in, which this noise down here is. But it's just it's Node, so you npm install it, and then like you require it up here, and then you can set it up and start it and handle things for like when client connects, when a message is published, those types of things. So it's just Node at this point. Any more? Yes.
Other than IoT, this would be a good implementation for, say, logging. If you look at some kind of real-time logging and monitoring real-time logs.
Maybe, and I hesitate when I say that, because even though this is built to be reliable, you always have to guard against what happens if a message does drop. Even with the guarantees, the QoS guarantees, maybe the device has been trying to send a message to the broker, but the broker doesn't get it, or maybe the broker gets reset or something. There's always some possibility that a message can get dropped. So with that in mind, maybe it's good for logging if you're okay with certain log messages not making it to the destination every now and then. All right, I think that's it.
Cool.
Thank you.
All right, everybody say bye to the stream.